Okay, sorry for a late start. Who knows, we might compensate for it with an early finish. Oh, we seem to be missing some. Wait, 1, 2, 3, 4, 5, 6, 7, 8 people out of 12. Yeesh. Oh, well, I did hear from one that they were not going to be here. And where on earth is everybody else? Well, hopefully they'll appear soon. Now, today will be the last new material that will be featured on the test. So Wednesday's class will be all about review for that. So if you haven't looked at the practice test, please do. And also go over the quizzes. I know I still have some quizzes to grade, or a bunch of them, so I will promise I'll get on that very soon. And then, as far as the homework is concerned, so a couple people turned in homework too. We'll see if we can have some time for questions for that to get everybody else in. Now, for following homework, if you look at the assignments, because the next homework is not due for a while. On the other hand, these sections are on the test, so I would encourage you to at least take some time to dive into these problems that are wrapping homework 2 before the test. But again, if you know how to handle the problems in a practice test, then you'll be okay. So it's up to you, but I would encourage you to not let this wait entirely until, well, for instance, certainly the MATLAB coding portions, any of those can wait. Okay, and certainly the practice test should be the major focus of your preparation. But okay, and so on Wednesday we'll talk about the practice test, any questions you might have based on after seeing the solution, and I'll give us some general tips for working problems in these categories. Be sure to examine the quizzes for all the Chapter 3 sections. For the lightning round questions, the conceptual questions, that'll be at the end of a test. And really, that's your best way of studying for that. Okay. Now, so there's a portion of some material that is not actually in section 3.4 itself that I need to cover first, but I will tell you where it can be found in the book. Oh, I don't want that one. Okay, this one. So we have Appendix B, a review of linear algebra. So there'll be a couple of sections of this appendix that I need to get into for today's material, and that deals with where are they here? Okay, vector and matrix norms. Okay, so I'm gonna deal with that first, and then we'll get into the rest. Okay. All right. So now we know how to solve AX equals B. We have various methods: Gauss elimination, Cholesky factorization, etc. I want to have some understanding of how accurate these algorithms are. Now, the algorithms as carried out on paper would be exact, but we have floating point arithmetic to contend with. So each operation is going to introduce some error, so we want to be able to have an understanding of how large that rounding error can be. Okay. So for this, we need some notion of magnitude for the various objects we're dealing with, vectors and matrices. And for numbers, we have absolute value. So how do we extend that concept of absolute value to vectors and matrices? So we'll start out with vectors, because that's the simpler, and then we'll go to matrices from there. Now, so from calculus, you did have to deal with concept of magnitude of a vector. So if you have, I don't seem to have the right package in here. What is it doing? Okay. Okay. Wow, it worked. I didn't actually expect it to. All right, yeah. So here, I needed a fancy symbol for real numbers. So you have a vector of real numbers. So can anyone remember from calculus how you defined? So if you have a vector of components x1, x2 up to xn, in calculus you dealt with vectors like that in only 2 or 3 dimensions, but in any number of dimensions. What would the magnitude be? Yeah, square root of what?
The component, summation of the component square.
Yeah. And the notation I was using in the calculus text that I most recently used here was, again, still using absolute value signs. Okay, I'll just make this a display equation. Yeah, so square root of the sum of squares. And that will work for us. We can use that as a notion of magnitude as well, at least for vectors. But there are other ones too that are also quite useful. So, glad you can make it. At least you haven't missed much. I got a late start too. Okay, so any function, and I'm going to use the double bars, just because it looks nicer. So the dot means placeholder. So we're taking applying this function to a vector x, and the output will be a real number. So any function from vectors to real numbers is a norm if it satisfies these conditions. All right, so there are 3 of them. So first, if you have any vector at all, the norm of a vector cannot be negative, and the only time that the norm is equal to 0 is if the x is actually the 0 vector. Otherwise, it'll be strictly positive. And this goes for complex vectors too. Again, it's going to be a non-negative real number, even if a vector itself is complex. Okay, so that's one condition. Next, suppose I have a vector and I scale it by some constant factor c, which also can be real or complex. then that has to be equal to what you get if you just take a magnitude or norm of x, and then you multiply that by the absolute value of c. All right. So scaling a vector has to scale the norm by the magnitude of that scaling factor. Okay. And then finally, what you know of as the triangle inequality, that the norm of a sum has to be less than or equal to the sum, not the product, the sum of a norm. So as long as the norm function satisfies the triangle inequality, it also is a valid notion of magnitude. Okay. So these conditions are satisfied by p norms, also known as I'll describe the book, LP norms. And this is a generalization of this notion of magnitude that you see here. So the p norm of a vector is equal to, so we take the sum of the absolute value of a components raised to the p power, sum them all up, and then we raise that to the 1 over p power. So in that sense, the notion of magnitude that you're used to, that's just the 2 norm. But we can define this with all different kinds of p. Okay. So here are some key values of p that are often used. Okay, so first we have the 1 norm. So that is just the sum of the absolute values. All right, so very straightforward. And then we have the 2 norm. So I'll square the sum of squares. Oh, something went wrong there. Okay. Now, you might find it strange that I'm putting absolute values in here. The reason for that is to accommodate complex vectors as well as real. So we're taking if it's a complex number, we're taking the modulus of that, and that's what we're squaring, just to make sure that everything turns out real. And then finally, the infinity norm is particularly useful. So what happens is, as you increase p, that tends to give more and more weight to the largest entry, largest element of a vector. So if you take that to its extreme, you're just taking the absolute value of the largest element of a vector. So that's what the infinity norm is. Now, one consequence of this is that if p is greater than q, then the p norm is less than or equal to the q norm. Okay, because if you look at the extreme of infinity norm is going to have only the largest element, whereas all of these have also the absolute value of the largest element, plus other stuff. So just to keep in mind that that we have these relationships. However, all p norms are equivalent in this sense, that if I have any two norms, p and q, that the p norm is bounded below by a constant times the q norm, and bounded above by another constant times the q norm. For constants c1 and c2, they're independent of x. Okay. Now, why does this matter? Okay, so this is important for convergence of a sequence of vectors. So I'm going to take a little time to explain what is meant by that. Okay. So I could say here, if p happens to be greater than q, then the constant c2 would be equal to 1. But then there'd be some other constant over here. The constant might depend on the dimension of the space. Like if these are n vectors, sometimes the constant might be n over square root of n or 1 over square root of n, something like that. That's okay, but it's still independent of x itself. All right. So a sequence of vectors xk converges to some limit x if we can define this convergence in terms of norms. Okay. All right, because if xk is converging to x, then what will happen is this vector between the bars will converge to the 0 vector, which will have a norm of 0, no matter what norm you're talking about. So because norms are equivalent, you're not going to have a situation where a sequence converges in one norm, but not in another. So for purpose of convergence, it doesn't matter which norm you're using to, for example, find the limit or prove that sequence of vectors converges to a limit. If you show that it works in a particular norm, like a 1 norm, you therefore know by this equivalence it's going to work in a 2 norm also. It may converge at slightly different rates, but convergence will happen. So at least you can trust that and not have to prove it again and again in every single norm. Because wow, what a pain that would be. Okay. All right. So that's the deal with vector norms. Now, matrix norms, those are a little more difficult to wrap your head around. So brace yourself. Okay. Now, so the definitions of matrix norms, unfortunately, are not quite so straightforward. So given a vector norm, the induced or natural matrix norm is defined this way. So I'll choose a general p, just for, so it could be any of the indices p that I showed, or any other valid vector norm. So we're taking the supremum over all non-zero vectors x of vector norms. So AXP over XP. Okay, so in other words, it's now the supremum, you may recall from another class, is the least upper bound. So essentially, it's the largest that this ratio can get. Another definition that might be easier to work with is the maximum over all vectors in space of unit length, unit magnitude, the norm of 1. And in that case, you just have AX. Okay. A technicality, the reason I can say max here, but I cannot here, is if we look at the set of all vectors that have a norm of 1, that's a compact set, closed and bounded. A continuous function, which the norm is, on a compact set is guaranteed to have a maximum and a minimum, where the supremum over all non-zero vectors x in the whole space, so everything except the origin, that is not a compact set, therefore not guaranteed to have a maximum. Okay. All right. Okay. So if I want to describe like the one norm of a matrix, or the infinity norm of a matrix, something like that, I can't just use the formulas that we have here. It doesn't work out that way. I need to apply this definition and hopefully get a formula from that. So what I will do is I will show you formulas in a few cases. And it's actually kind of a pain to prove that these formulas result from this definition of a natural norm. And so unfortunately, I won't be able to take the time to do that. I want to check if I did do that. Okay, I need to mention that too. Okay, for matrix norms. Okay, so I do show a proof of a formula for the one norm, and the infinity norm would be similar. Okay. All right. But I just realized that one key point about vector norms I forgot to mention. So this is just for the 2 norm. This is a property that is so important. It comes up in so many proofs and such that it deserves mentioning. All right, so what I have here on the left side is the absolute value of the inner product or dot product of x and y. And that is less than or equal to the product of the 2 norms of x and y individually. Okay, here H is the Hermitian transpose. I have to use that in the case of x and y being complex. Otherwise, I would just use a transpose. All right, but here we have dot product where if it's complex, you have to take a complex conjugate of one of the vectors involved. By convention, the left vector. So the magnitude of a dot product is less or equal to the product of the magnitudes. Okay. now, okay, that's some matrix stuff. Okay. All right. Actually, I think I will take a little time. How you prove this, because it shows how you can work with norms and certain properties, at least a 2 norm anyway. It won't necessarily apply to other norms. Okay, so if I look at this expression, so this is a 2 norm of x minus a constant c times y. So any scalar or constant c. Now this, keep in mind, whoops, that should be a 0, not a 9. That'd be kind of weird. Because it's a norm, it has to be non-negative. Now, a way to describe the 2 norm of a vector squared is the dot product of that vector with itself. Okay. Now, so that's something you take as a definition. In fact, I will put that up here. The 2 norm is equal to square root of the Hermitian transpose of x times x. So square of a dot product. Okay. So now, what I can do, due to the linearity of the dot product, this is the same as x Hermitian transpose x minus, and okay, to simplify things, I'm going to assume that everything is real. Otherwise, this won't work as nicely as I want. So I'm going to have C y Hermitian transpose x minus C x Hermitian transpose y plus C squared Hermitian transpose of y with itself. Okay. Now, Hermitian transpose of anything with itself is a 2 norm squared. So that's the first term. And the last term also. And then in the middle, well, the dot product of real vectors is commutative. So I can take advantage of that, and we actually have like terms. So I have minus 2c x Hermitian transpose y. Okay. Now, the thing is, here I have an expression that is quadratic in C, but the whole thing is non-negative. So if I wanted to, so the right side, all right, so which has roots, so I could use a quadratic formula to solve for C in a way. If I set this equal to 0, and what I have is, okay, so my coefficients a, b, and c, a would be the norm of y squared. I have a 2. Okay. I just realized I've been negligent of my subscripts. I need to make clear this is the 2 norm squared. Okay. Now, the rest of the quadratic formula will give me some minus b, so 2xhy, and then plus or minus square root, and I have my discriminant underneath. So that's going to be b squared, so that's going to be 4x dot product y squared minus 4ac. First for x and then for y. Okay. So those are the roots, which of course roots can be 0 or it can be real or complex. But the thing is, the only way that the whole expression is non-negative. So the only possibilities for roots are the roots are complex. So then it doesn't touch the x-axis at all. Or we have a double root, so a parabola touches the x-axis, doesn't cross it. So both roots are equal to 0. So in other words, so because the whole quadratic is non-negative, that means this discriminant must be non-positive. So this whole thing must be less than or equal to 0. So if I set this whole thing apart under the square root less than or equal to 0, and then simplify, take a square root of both sides, I get exactly this inequality. So QED. But this is a common approach in proofs trying to show various inequalities. If you can describe something as a quadratic, where the whole expression is non-negative, you can use what that tells you about the discriminant to prove whatever it is you're trying to show. So I've actually seen this useful in other situations, not just for the Cauchy-Schwarz inequality. Okay. This does apply if the vectors themselves are complex. It's a little nastier, so I wouldn't have time for that here, unfortunately. Okay. Now, what are some matrix norms? All right, so I have 4 that I can mention. Corresponding to the vector norms I gave earlier. So the one norm of a matrix alright, so assuming a matrix is m by n. So not necessarily a square matrix. So it's going to be the maximum over all columns of the absolute sum of the absolute values of all the entries in that column. So in other words, it is the maximum column sum. So you sum the entries in each column, absolute values. Whichever one of those column sums is the largest, that is the one norm. So the one norm of a vector, you're summing the absolute values of all the elements. You're not doing that here. You're not summing the absolute values of all the elements of a matrix. You're doing that in each column, and then seeing which is largest. Okay. The infinity norm. Whoops. The infinity norm of a matrix is very similar. That is the maximum row sum. All right, so you sum all the entries in each of the rows. Whichever row has the largest sum, that is the infinity norm. Okay. So the proof of a one norm that has been worked on in the text, and what it deals with is, okay, so it's on page 634. So what happens is I'm trying to find out how this quantity is when it is largest, assuming that the vector x has a one norm equal to 1. And what you're doing is I'm using a formula for a matrix vector product. But then by the triangle inequality just for plain old absolute value, I can express it like this. And what do we have here? This is the sum of all the entries in a column, because j is fixed and I is going from 1 to m. And because the sum of absolute values of all the entries of x is equal to 1, that's what allows me to just drop this part out. So that's the basic idea behind proof of a matrix norm for one norm formula. A similar approach can be used for the infinity norm. Again, using a formula for a matrix vector product. Okay. Now, unfortunately, the 2 norm is not so straightforward. So that is a square root of the largest eigenvalue of A Hermitian transpose A, and which is also equal to the largest singular value of A. Unfortunately, I've not had a chance to cover singular values. Okay. What is it complaining about? Oh, okay. Oh, I see. I forgot this. Okay. But we have here, this is, so if you take A Hermitian transpose A, largest eigenvalue, which is going to be a real number, but the square root is the 2 norm of A. Now, a big problem with a matrix 2 norm as opposed to a vector 2 norm is for general matrix, that requires order n cubed floating point operations to get the largest eigenvalue with very high accuracy. In some cases, you may be able to pull off a good estimate with order n squared work, but n cubed is generally what you'll get. So that's really a pain. So it's much more expensive to compute than the 1 norm or infinity norm, which require order n squared work. Also, this is an iterative method. You need it to converge. So not only is it that amount of time, but you're not really sure when the algorithm is going to end. In some really nasty cases, it may even fail. So for matrix norms, it's better to use a 1 or infinity norm. However, now there is a norm function in MATLAB, so you can do like norm of x or norm of a. The default for MATLAB is the 2 norm. So if I make I'll make a random matrix of integers. Okay, so if I take, here's how I can Okay. Let's do it again. All right. So I take the norm of A for one norm. Okay, 11. So I sum the entries in all the columns. This column, entries add up to 11. Here they add up to 10. And here they add up to 7. So that's for one norm. For the rows, I get 12 for the first row, 8 for the second, and 8 for the third. So I could do norm A infinity. So that's the infinity norm, and you get 12. Whereas if I do the norm of A by itself, that'll get. Oh, sorry, I had it in rational format from what I was doing earlier. Okay. Or I could here I explicitly specify the two, but you can see that's the default behavior. Okay. Now there's one more norm that's worth showing. This is actually not based on a vector norm. It's called the Frobenius norm. That's leading to the subscript f. And fortunately, it does have a straightforward approach to computing it, unlike the 2 norm. You take the sum of squares of all the entries of the matrix and then take a square root. So it's like if you took the matrix and you flattened it out into a vector and then took the 2 norm of that vector. So still does not correspond to the 2 norm at all for matrices, but at least this one can easily be computed. So the way you would do that in MATLAB, I could do norm A fro, and still take the sum of squares of all these entries and then take the square root of that. So that's the usage in MATLAB. Okay. All right, so Frobenius norm is not induced by a matrix norm. Okay. So now we have various notions of magnitude for a vector or a matrix. So now I want to show how these are used for the purpose of error estimation. Okay. All right. All right, I'm not going to use that. Okay. So, well, actually, maybe I can. So, a concept covered in 465-60, backward error analysis. The approximate solution of AX equals B is the exact solution of a nearby problem. And the way I'll do this is so a nearby problem will be one where the matrix A is perturbed, and I could assume that B is perturbed also, but to simplify things, I'm going to assume it's just a perturbation in only A. So if we let epsilon equal 0, then we're back to AX equals B. Okay. So the idea is, suppose my approximate solution is really x of epsilon for some epsilon. And it is the exact solution of this problem. Whereas plain old x, or x of 0, is the exact solution. So how big is x of epsilon minus x? So how large is this quantity? Okay. So, I want to try to at least get some sort of inequality for this. All right. So, so first I can do some algebraic rearranging. So what we have here is x of epsilon is equal to A inverse times B minus okay. This might not quite work the way I wanted it to. Okay. So now what I'll do is I'm going to subtract the exact solution from both sides. All right. And then, okay. And then what I'll do is take the norm, any vector norm, so I'm not going to specify, of both sides. Okay. And then I'm interested in relative error. So I'm going to divide both sides by norm of x. Okay. Oh, something went wrong parentheses wise. Okay. A inverse B minus EX of epsilon. Okay. Okay. Good. Now, okay. This is what I get for doing this sort of thing on the fly, but of matrix norms. Matrix norms have to satisfy the same properties that vector norms do. Matrix norm must be non-negative. If you scale a matrix, it scales the norm. Matrix norms has to satisfy the triangle inequality, but they also have this property, the submultiplicative property, that if you take norm of a product of matrices that is less than or equal to the product of the norms. So that's something that we can make use of here. Okay, so now if I take that expression and continue working with it, various properties of norms, I can break this up into various fractions. Okay, so what I'll do is make some copies of a right side. Because I have 3 terms altogether. But now I'll strip them all down. Okay. Okay. Then here I will not have the A inverse B. Okay. Oh. Hold on. I'm going to leave this there. I mean, I don't need this other term anymore. Okay. And the nice thing about this is, dealing with the exact solution, X is A inverse B. So before I even do anything else, before I even use any properties and norms, I can get rid of this entirely. Since that deals with the exact solution. And now I can focus on this. So here is where I want to use these various properties and norms. So first, I'm going to pull out the epsilon. So now I can get rid of it in here. Okay. And then I have, well, I don't need the minus. And then what I'm going to do is I'm going to multiply and divide. Dang it. By the norm of A. Okay. And then, using a property of a submultiplicative property, okay. So now I've pulled the norm of A inverse out, and I can do that as long as I have a less than or equal to here and now. Okay. Now, and also this part here, I can separate the norm of E. Okay. Now, so what I can do is break this up into the following quantities of interest. So I have epsilon, and then kappa of A, which I'll define in a moment, and then I have norm of E divided by norm of A times the norm of my perturbed solution divided by the norm of the exact solution. Okay. Where kappa of A is equal to the norm of A times the norm of A inverse. And that is the condition number of A, which is actually consistent with the notion of condition number that was discussed in 46560 for more general problems. It's how the backward error, error in the input is amplified to cause error in the output. So what we have here, the epsilon and norm of E, norm of A, that is the relative change in the matrix, the relative perturbation in the input. Here is the relative change in the solution. This part, because epsilon is small, this part is largely essentially going to be equal to 1 anyway. But the point is, the error in the input, so epsilon norm of E over norm of A, is amplified by a factor that could be as large as condition number of A, norm of A times norm of A inverse. So intuitively, the error in the problem, so errors in A, errors in B, like measurement errors, can be amplified by as much as A and the error in the solution. So if this quantity is large, we say that A is ill-conditioned. And that can definitely happen. It actually does happen in matrices of important applications, of course, because why not? For example, if you're solving systems that arise from partial differential equations, we're solving at the high resolution, those matrices tend to be quite ill-conditioned. So ill-conditioned systems are difficult to solve for any method whatsoever, like the direct methods that we have been seeing in this chapter, or the iterative methods that we'll be seeing pretty soon. That it's just a mess, and a lot of research is done to try to solve these systems more accurately, or maybe transform the original problem into one that is has better conditioning. Because what happens is the error can be larger for these cases because there's greater accumulation of round-off error. The matrix is it's close to a matrix that is not invertible at all. So we have so what can happen is you might have growth in the entries of U as a result of your Gaussian elimination, even with pivoting. Now, pivoting at least keeps the multipliers in check, but you may end up dividing by quantities that are close to zero. It's just all kinds of things can go wrong when it's a ill-conditioned system. And to give you an example, okay, so here I've made up two matrices that are fairly close to each other, but there's nothing obviously different about them. But one on the left is well-conditioned. Condition number is only 10. By the way, the smallest condition number possible is 1. Like the identity has a condition number of 1. But this matrix has a condition number of 10 to the 8th. So this is really nicely conditioned. This is horribly conditioned. So then I solve two systems of equations. So here I have B1 and B2, two B vectors that do not differ by very much. So what I do is I'm going to take A2, the ill-conditioned matrix, and solve systems with both B1 and B2. So B1 and B2 differ by about 10%. But look at the solutions. Here's a solution x1 and x2. The numbers are enormous in x2. So a small change in the input to the problem caused a gargantuan change in the output. Now, this is like a worst case scenario, and I actually know how to trigger those. So it doesn't always turn out that badly, that a change of this magnitude is not always going to lead to a change of this magnitude, but the point is it can happen. And in any given problem, so you have to be aware of that possibility. Okay. The other thing to keep in mind is, so if, as I mentioned earlier, if A is ill-conditioned, it is close to a singular matrix. All right, so this is more reliable than the determinant of A, and determining near singularity. So here's an example. This matrix here, 1's on the diagonal, minus 1's above, 0's below, upper triangular. The determinant is a product of all diagonal entries. So the determinant is 1. So you think, oh, that's not near a singular matrix because the determinant is not near 0. But the condition number is fairly large, so it's nearly 2,000. So you can tweak this matrix by just a little bit and get something that's singular, even though the determinant is not near 0. The reason why the determinant is not a good measure is that it's not scale invariant. Like if I multiply all the entries of this matrix by 2, then it would scale the determinant by a factor of 2 to the 10. Whereas the condition number, if you scale the matrix, it doesn't change the condition number at all. Because scaling the system should not change how well or ill conditioned it is. All right. So the condition number in MATLAB, you can use cond of A to get the condition number. Or you could do cond AP to use the P norm. So condition number by default is computed using the 2 norm, just like the norm function does. But you can specify a different norm if you want. But one difficulty about computing the condition number, it requires the inverse. And the inverse is a real pain to get. So the condition number command in MATLAB is not fast. Even if you're using a norm that's easier to compute, like a 1 norm or infinity norm, it still has to compute the inverse and then take the norm of it. So it's going to be expensive. So not recommended for code that you really want to run fast. Okay. All right. I just need to be able to see what I'm doing here. Okay. All right. Now, the last thing I want to mention. So let's do an approximate solution to Ax equals b. The residual is labeled R, and it's just basically substituting the approximate solution into the equation. So you look at b minus ax. So if x has the exact solution, your residual will be 0. That's what we want. So the residual, can be used to judge whether the approximate solution is accurate. But it is not the error. The error is, I'll define it to be E, and is equal to x minus x hat. That's what we really want to be small. So now I'm going to take this equation for the error, E is x minus x hat. I'm going to multiply both sides by A. So AE is equal to AX minus AX hat. But AX is equal to B, because X is the exact solution. So we get B minus AX hat, but that is equal to R. So that's how the error and the residual are related. A times the error equals the residual. So now, from the error being equal to A inverse times the residual, we have a following. If I take the norm of the error divided by the norm of x, so that is equal to, or less than or equal to, we have the norm of A inverse times the norm of R divided by the norm of x. Then, if I multiply top and bottom by the norm of A, okay. So what happens here is, up top, I have a condition number. Cap of A. Now, the AX is equal to B, but the norm of B is less than or equal to the norm of AX. But what that means is 1 over norm of A, norm of X is less than or equal to the norm of B. So now I can say that for relative residual, so you divide by norm of B, and the relative norm of the error, where you divide by the norm of x, are related by the condition number. So, just because the residual is small, dang it, stop it. So a small residual does not mean a small error, because what if A is terribly ill-conditioned? Then the normal residual might be small, but the error might still be very large. Okay. Like that. Norm of B is less than or equal to norm of A times the norm of x, because B equals AX. So if I take 1 over both sides, then that reverses the inequality. So 1 over norm of A, norm of x is less than or equal to 1 over norm of B. So that was used in these steps. All right, so if you have an approximate solution, you can always do B minus AX, and you'll get a small number most likely. But keep in mind, it's still not, the error is not necessarily that small. Okay, I just realized I've gone past time. So what I will do is, if anyone has homework questions, then we can handle that individually. And certainly there'll be time on Wednesday also. So if you don't have any homework questions, you may scram. Yes.
So is Wednesday going to be just for review, or we're going to continue with the scaling?
Oh, that's not even on the test, so I'm not going to cover that.
Okay.
It's not on any homework either.
So
Yeah, that's like an optional topic.
Wednesday is going to be mostly just test review questions from the.
Yeah, review and questions about anything, whether it's a test or homework. Yeah. Yeah.
2020. Number 20.
Oh, okay. Okay.
Wait, so when I wrote my code and I submitted, I didn't realize you had to put an error statement. The matrix is not singular.
Oh, okay.
I was singular right there. So I didn't really reach that part.
Oh, okay, right.
And I submitted.
Yeah.
So I was trying to add that part and resubmit.
Oh, okay.
So I realized that how do we check if the matrix is singular?
Okay, so what will happen is, suppose you go ahead and do pivoting, And so you move largest entry in that column into the diagonal position. If that diagonal entry is 0, the matrix is singular.
Yeah, I thought of that. So
Okay, yeah. Yeah. Yeah.
But I don't know what is it doing first. Is it checking if the diagonal is?
Well, because the thing is, it's not really practical to check up front. You're just going to go through the whole process trying to do Gaussian elimination. And if you find that you're about to divide by 0 and getting your multipliers, that's when you catch it. So you would so you can use MATLAB's error function.
So what I'm thinking is, how do I catch it? Because the diagonal entry may be 0, and I have to give it to it. It's no longer 0.
Well, so what can happen? Oh, sorry, what?
Like if after the first elimination, the diagonal entry is 0.
Yeah.
It will be non-zero under the diagonal. So when we pivot, it's no longer 0.
Oh, well, in that case, the matrix is still non-singular. It's after you pivot, if a diagonal entry is still 0, because basically what would happen is, if after you've eliminated what you can, and you get to a point where you're checking out a whole portion of a column and every single entry is 0, that's when it's singular.
The reason why I'm not sure how the code would work.
Yeah. So what you can do is right before the point where you're going to compute a multiplier, and so you're about to divide, you can have an if statement right there, and say if the thing you're about to divide by is 0, then that's when you'd abort, and you can use the error function and a message saying it's singular.
Then you also talk about the dimensions. So you mean like if it's not n by n matrix?
Yeah, so if a matrix is not square, or if B doesn't have the right number of entries to match A,